Greetings to you. Welcome to Physics with Ben. Don't forget to subscribe, like, share, and comment. We want to look at a brand new topic in today's video. Let's write. Current electricity. It will interest you to know that I am very particular with the nature of the videos I produce on the internet. This video is a video on a topic that comes up almost every year in your life. Don't forget to subscribe and share this video to those that need it. Thank you and stay tuned. So let's begin. What do we mean by current electricity? I also have a video on static electricity, that is electric field 1, Coulomb's law. This one is on current electricity, Ohm's law. So this is simply what? Ohm's law. But we are coming to that later. Electric current is simply defined as the flow of charges in a conducting material. This guy, Charles Coulomb, was able to give us a mathematical equation for electric current. I say it again, electric current is defined as the flow of charges in the conducting material. That conducting material can be a wire, or can be liquid, or can be anything that can conduct electricity. You know, we have conduction of electricity through solid material, that is Ohm's law. Conduction of electric current through liquid material, that is Faraday's laws of electrolysis. And then we also have conduction of electric current through gases. For this particular video, we are concentrating on conduction of electric current through what? A solid material. So we write that from Coulomb's, he defined the quantity of electric charge as Q is equals to IT, where your I is given as what? Q all over T. The symbol I is a symbol representing electricity in physics, and the unit for electricity is the ampere. That is that for that. We want to look at electrical resistance. Just that I keep telling my students that a car without a brake is a very dangerous car. So a circuit or an electrical circuit without resistance is also a very dangerous circuit. So just like the brake functions in the car, that is the same function of resistance in a circuit. Although the brake can stop the car completely, but resistance cannot totally stop the flow of electric current. It can only reduce it to a very minimal value. So electrical resistance is simply the opposition to the flow of electric current. The electrical resistance is measured in the units of ohm, named after the guy who discovered it, George Simon Ohm. And the symbol for the electrical resistance is R. While the unit, the letter for representing the electrical resistance is the R, while the unit is the ohm, and then the symbol is something like this or something like this. We are coming to this later. So we have looked at electric currents, electric resistance. Let us look at electrical symbols for right now. Electrical symbols. It is very important for us to know electrical symbols, because when you don't know them, you'll be unable to identify them in a circuit. You'll be unable to even draw a circuit correctly. So let's start with the first one. We are going to start with electrical resistance. Or let's say resistor. Just write resistor, sorry. Let's write resistor. The resistor is ending with R and with the units ohm. Before I talk about this guy, I want to say something quickly. There are two types of resistors. And I'm going to draw them on the board and show you how they look like physically. We have the variable resistor. We have the fixed resistor. So for the fixed resistor, this is the two symbols that we have for them. These are the terminals. Or you may go with this one. This or this. For the fixed resistor, we mean a resistor whose value is fixed. Now, what is a resistor? A resistor is an electronic device that opposes the flow of current. This is the symbol for a fixed resistor. As you can see, we have 2 ohm written boldly on it. This is the symbol for a fixed resistor. The other one is the variable resistor. The variable resistor is also something like this, but then you have an arrow, a stroke here. This or this with a stroke here. As the name implies, a variable resistor is a resistor whose resistance is not fixed but varied during experiment. We have the resistance box as one example of a variable resistor. That is it. This one, I don't normally use this one for my experiment because the values are not too wonderful. We also have this as a variable resistor. Then we also have the rheostat. I don't know if you have seen it before. This is a rheostat. It's an example of a variable resistor. You can see it very well. So these are the examples of a variable resistor that we have here. Standard resistor. The second one is what? Variable resistor. The second symbol I want us to look at is the ammeter. The ammeter is represented with a symbol like this. A 0 and an A inside it with 2 wires, connecting wires at both ends. The ammeter is an electrical device, this is it in my hand here, that is used in measuring the electric current in ampere. This is it. So the next one is the voltmeter. The voltmeter. The voltmeter with this and this. The voltmeter is an electrical device that's used in measuring the potential difference in the circuit. This is the symbol, this is the device I'm holding in my hand. This is it here. The next one I want to look at, that is number 4, is the cell. The electrical cell looks like this. The terminals at both ends, the plus and negative side. This is what we mean by a cell in physics. This side is the positive side. This is it here. And this side is the negative side. This is it here. So here on the board, this is how it looks like, a cell. The other one is a symbol for the battery. This is number 5, the symbol for the battery. The symbol for the battery looks like this. A battery is simply the combination of 2 or more cells. So if I join these 2 guys like this, we call it a battery. This is it. So on the board, this is what you have. The next one is the electrical key. The key looks like this. is the key. I'm going to just stop at the symbols that are particular in this topic. There are other thousands of electrical symbols, but for this particular topic, we don't need them right now. The symbol for the diode, for the transformer, for the bulb, and all of that, we don't need them right here, right now. But these are the ones I will be using in this particular topic. So the next thing we're going to look at is electrical circuits. Electrical circuits. What do you mean by an electrical circuit? Just as we have the road network where our vehicles will travel on, so we also have the electric circuits that will allow currents to flow through them or charges to flow through them. The rail tracks to allow the train to travel on, so we also have electric circuits. So what do you mean by electrical circuits? An electrical circuit, right? An electrical circuit is simply a path that is provided for the flow of electric currents. An electric circuit is simply a path that is provided for the flow of charges. There are two types of circuits, namely open circuits and closed circuits. There are two types of circuits, namely we have the open circuits and then we have the closed circuits. I'll quickly draw this to explain what I mean. So this is an example of a closed circuit, an open circuit. This is my resistor, my voltmeter connected across the resistor. This is my ammeter. This is my cell. This is so this is my key, open circuit. It is open here. So when this key is not switched on, we call it an open circuit. So this is negative, this is plus. So the direction of flow of current will be in this way. And then if we close it, it will come back to this place. So this is an open circuit. So here is the voltmeter. Here is the resistor R. Here is the ammeter. Here is a cell. We always represent it with a V, voltage, or EMF, or sometimes E. So when you see E, V, or EMF, they all mean the same thing. Now I'm going to draw the same thing here, but then that will be for the closed circuit. If I have something like this, and then my voltage across the resistor, and then I have my ammeter here, and then my cell, and then this is close. Then I have my negative, my plus here, and then I have my R here. The current will flow this way. The current will flow in this direction. Back here, here, up, here, here, down, here, and back in here again. So this is my V. So this is my cell, the ammeter, the voltmeter, and then the resistor. So this is an example of a closed circuit. A circuit whose power is on, and a circuit whose power is off. Call it the circuit is broken. You break the circuits. You make the circuits. So these are the two types of circuit that we have in electricity. So we are going to look at arrangements of resistors in series and in parallel. Arrangements of resistors in series and in parallel. Right. arrangement of resistors in series and in parallel. First off, look at them what? As resistors in series. Right. When resistors are connected in series, as you can see on the board, they have the same currents flowing through them. But however, they have different potential difference across all of them. So this is my ammeter. Of course, I'm not going to use a cell now of a battery. 3 cells. I'm going to use 3 cells in the circuit, plus and negative. And of course, I'm going to use a closed circuit. So the current will flow in this direction. Here, back here, 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 here. So this is the diagram of arrangement of resistors in series. So when resistors are arranged in series, you have the same currents flowing through them. This is our V or our EMF, the battery. So but then you have different voltage. So this is the voltage across R1 from here to here. This is the voltage across what? R2, V2. And this is the voltage across what? R3. So this point to this point. This point to this point. This point to this point. So this is the voltage across this, the voltage across this, the voltage across this. So the total voltage in the circuit is given as Vt is equal to V1 plus V2 plus V3. All the units of volts. From Ohm's law, you know that V is equal to IR. V is equal to IR. So, since you're going to have the same current, we are going to say that our V1 is going to be V is equal to IR1. V2 is going to be IR2. And V3 is going to be what? IR3. That is that for that. Let's quickly look at what happens when. Okay, how about the combined resistance? Sorry. For the combined resistance, this is what you have. You have your RT is going to be R1 plus R2 plus R3. Now let's suppose that we have 4, 5, 6. 4, 5, 6. So our RT becomes what? 4 plus 5 plus 6. And that will give us what? Our RT equals what? 15 what? Ohm. That is how we find the combined resistance when resistors are in series. So let's look at resistors in parallel quickly. Resistors in parallel. When resistors are in parallel, as I draw on the board, when resistors are in parallel, what do you expect? Sorry. When resistors are in parallel, you have, I want to draw this in neatly. You have the same voltage, but then different currents flowing through all of them. This is the same voltage they all share. They share the same voltage. They share the same voltage. And so here will be your ammeter, and here will be your cell. Of course, it's going to be a closed circuit. So your plus, your negative, this is your V, this is your ammeter, this is your voltage, this is your R1, this is your R2, this is your what? R3. So this is your, also your I1, your I2, your I3. So the current will flow in this direction. The current will flow in this direction. Back in here again. This is the direction of flow of the current. So the total current in the circuit IT will be given as I1 plus I2 plus what? I3, all in ampere. Now, you're going to have the same voltage. So the combined resistance in the circuit will be 1 all over R1, 1 over RT is equal to 1 all over R1 plus 1 all over R2 plus 1 all over R3. Of course, if you want to find the total resistance, you're going to find the reciprocal of this. So that if you work it out, you're going to have 1 all over RT is the LCM then is R1, R2, R3. Yes, so that you have R1 plus R2 plus R3. So your RT is R1, R2, R3 divided by R1 plus R2 plus R3, all in ohm. This is how you go about it. Now, for V is equals to IR. So, they're going to have the same voltage. So, your V is equals to I1 R1. V equals to what? I2 R3. V equals to what? I2 R3. I3 R3. So these are the possible equations you will come in contact with when resistors are in parallel. The same voltage across all of them, but different currents, and that is that. So we're going to use this in another video for our calculations. So we're going to look at conduction of electric current through solid, and that is Ohm's law. Conduction of electric current through solid. So we state Ohm's law as follows. Ohm's law is a very, very important equation in physics. Law in physics. You don't know how to state it, you are in trouble. So let's write Ohm's law. In wire experiments, there are 3 basic experiments that comes up every year: electricity, optics, and mechanics. If you are running any experiment under electricity, it is likely you must state Ohm's law. Ohm's law states as follows. Ohm's law states that provided the temperature and other physical conditions are kept constant, the current flowing through a conducting material, e.g. a wire, is directly proportional to the potential difference across its terminals. So mathematically, Ohm's law states V is proportional what? To I. In this case, I is a dependent variable while V is an independent variable. I depends on the value of V to increase its value. So it is increase, increase, decrease, decrease. So removing this sign, we say that our V is equal to what? IR, where R is the resistance in the circuit. R is the resistance in the circuit. So if you are going to run an experiment, you know that Y is equal to MX. So we can rearrange this as V is equal to what? Ri, where your V is your Y, your R is your M, and your I is what? Your X. So a graph of V in volts over I in ampere will give you a straight line graph passing through the origin, where here is your change in V and change in what? Your I. So that the slope, because of what? Change in V over what? Change in I. And the value for that slope is simply what? The resistance in the circuit in ohm. That is that for that. So this law is very, very important in physics. I'm going to produce a video on this, on how to run experiment to verify Ohm's law shortly. Trust me. So we want to look at something quickly. We want to look at electrical work done in a given circuit. The electrical work done, in a what? In a circuit. The electrical work done in a circuit is simply the work done in moving a unit charge from a point of affinity from one point to another in an electric field. And in physics, we say that work is done when a force moves a load through a distance and in the direction of the force applied. In this case, the force that moves the charges is simply the EMF in the circuit. So right mathematically, the electrical work done, W, is given as what? Q times V. You can call this equation number 1. Now recall that Q is equal to IT. So we are free to say that W is equal to what? IT times V, or ITV. You can call this equation number 2. Also recall that from Ohm's law, your V is equal to what? IR. So we are free to say that W is equal to what? IT times what? IR. And if you do that correctly, you have your W to equal to what? I what? I square RT. You can call this equation number 3. You can still move on and on and on and on again to do all this. Take notes, don't be confused. You may see in other textbooks as H is equal to QV, as H is equal to IVT, as H is equal to I square RT. Don't be confused. They all mean the same thing. Electric work done is measured in joules. Electric heat energy, here stands for heat energy, is measured what? Also in joules. That is why we use both symbols for the same thing. Now this is perceived as, if you put on your electric bulb, if you go close to it, you start feeling heat around the bulb. That is the electrical work done, or the electrical heat energy generated in the circuits. So we want to look at quickly electrical what? Power. From power P is given as what? Work done all over time. You know, in the topic work, energy, and power in physics, we define power as what? Work done over time. But recall that we are talking about electrical power in this circuit. I mean, in this section, not the power when a boy is climbing a staircase and you have to calculate the power he dissipates in climbing the staircase. This one is electrical power. Now, the work done is given as QV. So we are going to say that this is equation number 4. But W is given as QV. So we are going to say that P is equal to what? QV all over T. Recall again that your Q is equal to what? IT. So it implies that P is equal to what? ITV all over T. This will cancel this T. And so this implies that your power P is what? IV. If you don't want, you can still move on. You know that V is equal to what? IR. You can say that your power P is what? I times RI. So your power P is what? I square R. So power is I square R in the units of watt. Everything here is in the units of watt. Power is I square R. Why not? Electric heat energy is what? I square RT. The T here makes it what? The electrical what? Heat energy. To this, we have come to the end of today's video on current electricity. I want to produce another video on static electricity. That is Coulomb's law. Static electricity. Watch out for that video. Watch it. It's going to be series 1, 2, 3. And then with this video, I believe you are good to go in everything that has to do with current electricity. I'm going to use all these equations in this video and video 1, 2, 3 on electric field 1 to do all the calculations in electricity. Current electricity and what? Static electricity. Don't forget to like, comment, subscribe, and share this video. I wish you good luck in your S9 exams. I'm expecting nothing less than A1 from you. God bless you and bye-bye.